Hello, everybody. In this particular video, we're going to talk about projections, in this case on general spaces, not just lines, or at least we'll begin that conversation. And in order to have that conversation, I need to introduce the idea of orthogonality in general. So you remember that we can project a vector v upon another line spanned by a vector u by just doing the projection operation. We've seen that there's a bunch of cool applications of projections, especially with lines. We were able to find the distance of points to lines by using projections. There's other applications too. But in order to get to the more interesting applications, we need to generalize this idea. To do that, though, there's a bunch of other little steps we have to do before we get there. But in general, let's get an idea where we're going. So suppose you have a plane and you have a vector not in that plane, and I want to project that vector v upon the plane P. Well, notice that in order to do so, I'd have to have a vector that's in the plane. So right away, how do we figure that out? Like, what should that vector be? And such a way that the difference between the vector and the projection, they have to be orthogonal to each other, right? They have to be perpendicular to each other. So the projection and v minus projection, we want that thing to make like a right triangle in space, if you think of it in 3 dimensions. Again, how we go about doing such a thing, how we go about finding that projection. So there's at least 3 questions. What do we mean by perpendicular in a space in general? Like, what does that mean? And then, is there actually more than one answer? Could there be more than one projection when you project a vector upon a plane or something else? And then how do you even compute the thing? So in order to do that, remember that when you project a vector upon a line, you actually use the vector that describes the line. So we're going to do the same thing here. We're going to use vectors that describe the plane, but we're not going to just use any old vectors. We're going to use vectors that are in some way orthogonal to themselves, perpendicular to themselves. So let's suppose that we have a set of vectors. These are non-zero vectors. We'll call them an orthogonal set if every pair of distinct vectors are always orthogonal. In other words, their dot product 0. So then vi dotted with vj is going to be 0 whenever I and j are different. If I and j are equal to each other, well, then that's actually the length of the vector vi, and we don't know what that length is, and we don't care. For example, these 3 vectors together, they make an orthogonal set. They make an orthogonal set because if you take the dot product of v1 with v2, you get 0. Take the dot product of v1 with v3, you get 0. And if you take the dot product of v2 with v3, you also get 0. So because this dot product is 0, and this dot product is 0, and this dot product, every single dot product, we have different sub-bases, the different indices. All those dot products are 0. That's what it means to be an orthogonal set. Pretty easy. So, but there's something neat about an orthogonal set. That's just a statement about dot products. Anytime you have an orthogonal set of vectors, they're instantly always linearly independent, always. The reason why is pretty easy to see. Suppose you have a linear combination of these vectors that add up to the 0 vector. Now just take any index, any I you like, and take the vector vi. What I want you to do is take that vector and then take the dot product of the vector in the equation you see on the left with vi. On the left, it's just vi dotted with that linear combination. On the right, you'd have vi dotted with the 0 vector, and that's just 0. On the left-hand side, all of this expression that you see here, you can expand that out because remember, dot products distribute through sums, and they distribute through scalar multiplication. So you would get something like that on the left-hand side. I've written it this way because if you remember, all these vectors are orthogonal. So if the indices, those index, if they're different numbers, the dot products are 0. So out of the left-hand side, there's actually only one dot product that matters. And it's this one, the one that's right here in the middle. All the other dot products, that would be 0, that would be 0. But vi dotted with itself is just the length of the vector squared. So the left-hand side just collapses completely to be ci times the length of the vector vi squared. But if it's an orthogonal set, then the vectors are not zero. So then the length of this vector is not zero. I can then divide both sides by this non-zero number to get that Ci must be zero. This is true for every I. So that means C1, C2, C3, up to Ck, they're all zero. And that's what we need to do in order to show you that these vectors are linearly independent. So that's neat. Anytime you have an orthogonal set of vectors, they are instantly linearly independent. Okay, well, if they're independent, then that means the span of those vectors forms a basis for the corresponding subspace. Because if you take the span of them, they're instantly independent. So they span the space, they're independent, they're a basis. So we will then say an orthogonal basis for a subspace is just a basis where all the vectors are orthogonal. Now, the minute they're orthogonal, of course, they're linearly independent. So the spanning part's the only additional thing by when you say it's a basis for a subspace. Just some examples. If you look at R3 and look at the XY plane, that plane is spanned by two vectors, I and J. But I and J are orthogonal to each other because they're dot product 0. So I and J makes a orthogonal basis. I have orthonormal here. That's actually true. An orthogonal basis for that plane. Also, though, these three vectors form an orthogonal basis for all of R3. Why? Well, because these vectors are orthogonal to each other. We just said that before. Take the dot product in any order of any of these guys. Their dot product is going to be 0, as long as you don't get a dot product with a vector with itself. So they're orthogonal. That means they're linearly independent, but there's 3 of them. Since there's 3 of them, that means then by the really super powerful theorem that the following are equivalents, the fundamental theorem of invertible matrices, this means that since the dimension of the space is 3, and I have 3 linearly independent vectors, they instantly span the space also, and are therefore a basis for that space. So then these 3 vectors, Q1, Q2, and Q3, form an orthogonal basis for R3. Now, a much more interesting question is, instead of just verifying that a bunch of vectors form an orthogonal basis for some kind of subspace, the interesting question is what if I give you a subspace? Can you get me an orthogonal basis for it? The answer is yes, but it's going to take us a while to figure out how to do so in a nice way. So I'm going to do it once where I talk out the reasoning behind finding an orthogonal basis for this particular subspace in R3, but restricting myself to only using what you guys know as of right now. In another video, one more video, like next class, I'll be able to come back and do this much faster. Much faster. I'll get a different answer, but it'll be much faster to compute. So I want to find an orthogonal basis for this subspace of R3. So the first thing would be let's just find the basis, right? Let's just find a basis. So you know how to do that. You just take the vector, you replace the variable x with what it equals in terms of the free variables in this case for the equation. You can then take that vector, in this case right now in terms of y and z, and rip it apart to get one vector times one free variable plus another vector times another free variable. This then means that every single vector in W can be written as a linear combination of these two, and they obviously are linearly independent. So then that space W is spanned by these two vectors, and they are definitely linearly independent. That's a basis. Unfortunately, though, it's not an orthogonal basis. Because if you take those two vectors and you take their dot products, U and V, that dot product's not 0. So what I want to do is I want to find orthogonal basis for W. This process I gave you to find a basis is not going to give you almost ever, really, ever, an orthogonal basis. So how can we fix it? So the idea is we know the dimension of W now is 2 because there's 2 vectors in its basis. So all I need is 2 vectors that are in W and are orthogonal to each other. So I'll make that easier. And among those 2 vectors, one of them is going to be U. I'm just going to arbitrarily pick it. I'm going to say U is going to be one of those 2 vectors. So I want another vector that's in W and orthogonal to U. So let's just say that W is going to be that vector. The vector W, whose components are X, Y, Z, is going to be a vector in W, the subspace, that is also orthogonal to the vector U. So then just putting it down again so you can see what I'm talking about. I want to go and find out then what is this particular vector? Well, I know the following things. I know that if you take this vector and you take its dot product with the vector u, it's got to be 0. So the vector x, y, z dotted with 1, 1, 0, that's just x plus y. And that has to equal 0 because these vectors are orthogonal to each other. But I also know that w is, the vector w is in w. It therefore has to satisfy this equation. So I now know that whatever this vector w is, whose coordinates are x, y, z, it has to satisfy 2 equations in x, y, and z. I'll just take that system of equations and I'll solve it. So w then could be a vector of the form which the first component z, next one is negative z, the next one is negative z. One such example is where z is 1. So these two vectors, 1, 1, and 1, negative 1, negative 1, these two vectors are definitely both in w, the subspace, because they satisfy the original equation. That being right here, they both satisfy this equation. So they're both in w. They're both obviously orthogonal to each other. So therefore, they form a basis for w. I know they form a basis for w because I know the dimension of w. Remember, the dimension of w was 2. So I only needed 2 linearly independent vectors in that space. So these two vectors are orthogonal, and they are already a basis. So they form an orthogonal basis for w. Is there a better way? Oh, yes. This is a really long way to do it. But as of right now, this is the best we have. Okay. We need one last thing. One last thing. One of the reasons that we want orthogonal bases, or just an orthogonal set, is it winds out that it's really easy to figure out the coordinates of a vector in the subspace spanned by these vectors. It just winds up being that the coordinate, if you want to know the ith coordinate, it's found by doing this particular computation. Why is that true is also really easy to see before I have to go and use this particular theorem. Because we're assuming that w is in the space spanned by the vectors in V. That means that w has to have this form for some scalars. All I have to do now, and I already know those scalars are unique too, because the vectors V form a basis. So we know that we have unique coordinates. All I have to do is find out what those coordinates are, what those components are. So take just the ith such vector, Vi, and like I did before, take the dot product on both left and right of that equation, on left and right of that equality, on the right by, let's say, Vi. If you do that, you get this. But again, remember, on the right-hand side, only one of those dot products matters, because if the indices are different, you get 0 anyway. So out of all that, the only one that matters is when you're looking at the ith term of that sum, and that would have been Ci times Vi dotted with Vi. And if you look at that equation and just divide by the dot product, Vi with Vi, you get the result right away. So this is fantastic. This is great, because normally to find coordinates, we have to solve a system of equations, and it's a pain. Here, we don't have to. It's just a bunch of dot products, and we divide them. And it's not even difficult dot products. So I'll show you what I mean. We'll do one. So we already know that these vectors q1, q2, q3 form an orthogonal basis for R3, because they're orthogonal, and the dimension of R3 is 3, and there's 3 such vectors. So they form an orthogonal basis for R3. I want to know the coordinates of the vector u in terms of this basis. So there's a bunch of entries. So you have C1, that would then be, I take Q1, and I take its dot product with U, I should not be there, and I divide by Q1 dotted with Q1. So in the numerator, that dot product would have been 1 minus 3, so that's negative 2. And the denominator, you have Q dotted with Q, that would then be 2, so that is negative 1. So for C2, that will then be Q2 dotted with U, and that's all over Q2 dotted with Q2. So that would then be U dotted with Q2. So that would be 1 plus 4 plus 3. So that's 4 plus 4, that's 8. And then you're dividing by the dot product of Q with itself. So that's 1 squared plus 2 squared plus 1 squared, that's 6. So that's 4/3. And then lastly, C3 would then be Q3 dotted with U all over Q3 dotted with Q3. So Q3 dotted with U will be 1 minus 2 plus 3. That's 4 minus 2, that's 2. And then you're taking Q3 dotted with itself. That's 1 squared plus negative 1 squared plus 1 squared. That's 3. So the answer is just 2/3. So we have to have then that U is equal to negative times Q1 plus 4/3 of Q2 plus 2/3 of Q3. That's what U has to be. And you can go back and just check it if you like. It's really pretty easy to do. So there you have it. So then if you want to know, then something's not right here. I did one of these computations wrong because it's actually not adding up to be U, right? No, that's you. I tried. No, I'm fine. I'm doing it correctly. So then you have that. You have that. And another way to write this, by the way, is you can write down the coordinate vector. Remember, we did this back in chapter 3. That's the coordinates of this vector relative to the basis B. That would be the vector -1, 4/3, 2/3. I'm bringing up these coordinates because we're going to need them later on. I want to keep them fresh in your mind. Coordinates are also a vector, and there's a correspondence between the vector and its coordinates, which we need to discuss. Okay. Now, just as a slightly different viewpoint, because it's always nice to connect different ideas in linear algebra, because the more you connect, the more cool things you can do. So that theorem I gave you about the coordinates can also be written this way. So if you, again, have an orthogonal basis for a subspace and let W be any vector in that space, then there is a unique linear combination of V in terms of that basis. Before I wrote down C1 V1 plus C2 times V2, but just go put in what I had for C1 and C2 and so on. You get this result. That W can be written this way as this scalar times V1 plus the next scalar times V2, all the way down to the last scalar, CK times VK. But the really neat thing is, don't think of them as separate. Don't think of them as a scalar times a vector. Put them next to each other. And when you do so, you should notice that that's a formula you've seen before. That's actually a projection. That's the projection of the vector W on V1. And in fact, all of them are. They're actually all projections. So that's really neat. It means then that the vector W can be uniquely written as a sum of vectors, where those sum of vectors are actually the projections of the vector W upon the orthogonal basis. It's really, really neat. That's important because in a little bit, in another video, like next class, you'll see that actually this is the projection. This is how we project vectors in general upon another space. You'll get the exact same formula. It'll be the exact same thing. It's just that the vector W won't be inside the space, but the idea is exactly the same. All right, I think that's enough for this particular video.